Did you know Yann LeCun dropped a rap album last year? Um, his latest album, titled Deep Learning, is a mix of rock, punk, and rap. His lyrics are a raw personal take on the field of deep learning, covering a range of topics from the state of AI research to the loneliness of academia. So check the lyrics here in the song. He talks about his vision for the future of AI. We got to think about the future. It's going to be here soon. Maybe we can even put some AI in the moon. Think about the children, think about the next generation. Let's make sure we put the right systems in their foundation. Absolutely, like, beautiful, touches my heart. Here it's all about the learning, it's all about the network, it's all about the training, it's all about the perception. Doesn't rhyme. Takes a better rapper than me to make this work. But this is a generation from a new model called Llama of Meta AI. There's other funny completions here. We can go over them later, but we want to go over the paper first. This isn't this is the latest paper in a series of the research of large language models. And the interesting thing is that they don't necessarily go larger and larger and larger, as we've seen, although that's also a conclusion of this paper, but they are trying to just get better with the available resources that they have. So the paper is called Llama 2L, spelled like this, Open and Efficient Foundation Language Models. The main authors are Hugo Touvron, Thibault Lavrille, Gauthier Issachar, Edouard Grave, and Guillaume Lampe. I hope I pronounced all the French names correctly right here. As I said, this is by a group at Meta. And the main thing is how can we train models that have a fixed inference budget? So we've seen a bunch of constraints recently, but this paper really tries to go about making models that are ultimately cheaper at inference, as they state right here. So they say, what if, ultimately, if you have a model, what interests you is how much you can generate from that model, how much you pay per token, let's say. And how it has been trained, how much you wasted training it, isn't really that important. Other papers focus more on that. So, for example, the Chinchilla papers, they focus very much on, if I have like a fixed training budget, how do I allocate it properly? Whereas I guess other papers just say, well, how can I get the best performance possible? And then, we scale up to 540 billion parameters. This model here says, well, for a given size, let's say 13 billion parameters, how good can we get at inference? And for the given size of 65 billion parameters, how good can we get at inference? So they release a series of models from 7 billion to 65 billion parameters, and notably, even the 13 billion parameters model right here, they say it outperforms GPT-3. So GPT-3 being 175 billion parameter model. Now, of course, what outperforms means and what even the term GPT-3 means nowadays, that's, I guess, up to you. They have a metric in the paper, and it very much seems like you can get away with smaller models if you train them smartly and you train them for long enough. Another conclusion of the paper right here is, they say, for instance, although Hoffman et al., that's the Chinchilla papers, recommends training a 10 billion model on 200 billion tokens, we find that the performance of a 7 billion model, so very comparable to the 10 billion here, continues to improve even after 1 trillion tokens. So the conclusion is just train for longer. And that's pretty much this paper. So if you came here expected like big scientific inventions, no, it's very much you do it in a smart way. You build large enough models in a smart way. It's an engineering challenge to train them for sure, but you do it for long enough on as much data as you can and high quality data, it will give you a good model. The other thing I want to point out here at the beginning is their immense focus on openness. They tweeted out on Twitter, we're open sourcing these models. And throughout that paper, they just continue to hammer this in, like how open they are. Oh, we release this to the community. Where is it? I can't find it right here. we release this to the community openly and freely and open sourcing and so on. What they do is they release the models under a non-commercial license. So it's like for research only. Now that's not bad, but it's not open source, right? Like, let's be clear. And I find this to be a little bit, I don't know. These people use Linux, they use Apache web servers. Even this paper is written by LaTeX. It's by PDF, LaTeX compiled. All of these things are actually open source. The Linux kernel, you can use it very much to do business. You can even use it to do bad things, right? And that is a main part of the reason why we're here today. Like, I'm pretty sure there's an argument to be made that the entire deep learning revolution, whatever you want to call it, would never have happened if people in the past behaved like these people right now. If Linus Torvalds just was like, well, I have the Linux kernel, but I'm just going to give you a compiler for it, right? And then I'm going to give you an 8-page PDF saying how I did it. like no. And the same thing, you probably wouldn't have a driver for NVIDIA cards to do CUDA computations, right? If the Linux kernel was research only or came with some usage restrictions that made it business unfriendly. You wouldn't have that. NVIDIA would not bother making drivers for their cards. And obviously, as you know, NVIDIA, they also don't let too many other people interfere with their stuff. So you all build on a foundation of people who have sat down and very clearly said, yes, it's the best for everyone if this is business friendly, because then it will be the most beneficial outcome, because the most work will flow into it. Yet people sit down and they themselves think, research only is better, or usage restrictions. We know what's good for you. Like, sorry, these are my quarrels. I'm done now ranting. I'm just, mind you, all of you are building on a foundation of actually open source things, actually open source software, without which you would never be here. And I am just a bit skeptical of not giving back in the same vein. Again, which is fine, but then don't get on the high horse and claim how open you are while not doing it at the same time. Also, to my understanding, people are still waiting for the llama way. It's like also very funny for how much they appraise themselves of how open they are. It's like, well, where are they? But I guess that's more like corporate stuff, like legal. If you ever are in a big corporation, to get anything out there, you need like 50 approvals, and then legal comes back and it's like, yeah. They probably had a big trouble calling this llama because it's a word and someone might have a trademark on it or so. All right. Let's dive into it. They say our training approach is similar to the methods described in previous work and is inspired by the chinchilla scaling laws. Again, chinchilla scaling laws specify that for a given training budget, how should you allocate it? And the conclusion is that maybe instead of going really big parameters, you might want to go into a bit bigger on data and amount of compute you do. Yeah, but we'll see in this paper. So they first go over their pre-training data. And there's nothing too special in here except that it's all fully open. So they make a big attempt, which is really cool, right? And don't get me wrong from before, it's really cool that people release the model openly. Like, of course, like even to the research community, it's better than what OpenAI is doing. Much better, right? It's just like, go the extra mile. All right, so they work with completely open data, which is also cool. So completely open data, most of it, as you can see here, comes from Common Crawl. There are a few more high quality data sets in here, which they then also sample more frequently. This, I think, has been a recipe throughout the last developments in these larger language models, is that even though you have enough training data available, you want to sample them in different proportions in order to achieve the best result. Wikipedia, for example, being fairly high quality data, probably also books being fairly high quality data, you might want to sample them more often than once. Sampling them twice will probably not deteriorate, like do any sort of memorization effects and it will still like up the quality of the final model. Although it is quite interesting that sampling it twice, well, I guess sampling it twice makes twice the difference. I wonder though also because a lot of the evaluation data, as we'll see later, comes from the fact like it's some language understanding task, like you ask the model a question answering and so on, which obviously something like Wikipedia or books would be very favorable as training data sets. So I'm wondering how much of the recognition that we should sample more often from these data sources is just due to the fact that it gives you better numbers on these evaluation sets, and how much is really due to the model becoming more performant downstream. I guess then you get into questions of how what humans want to do with the models, how much that overlaps with information that might be in Wikipedia. So it might be, again, like fairly fair to actually use that. All right, so I don't want to talk too much about the individual data sets right here. They are just aggregated from different sources, cleaned, and so on, and tokenized using a byte pair encoding algorithm. One thing they do is they split all the numbers into individual digits, because otherwise tokenizers might take numbers apart. So 858, for example, might be taken apart to 5, 8 being one token and then 8 being another token, which makes arithmetic very different if you have tokens 5, token 8, and token 5, 8 in your vocabulary. You need to learn to do math sort of between all the pairs of the different tokens. And therefore, it's much more ideal if you just split the number tokens all apart. Now, you're probably going to lose some other stuff. For example, I'm going to guess that years like 1999, having that as an individual token would make a lot of sense, because even us humans recognize that thing less as an arithmetic object, like an object to do math with, much more than an entity, like it's the year 1999 and stuff happened there. Most notably, the Matrix movies play there. So I'm not sure, but it seems to be. Again, you can ask how much is this due to some considerations of evaluation sets, and yeah, it's a tough topic. But they do as they do. Here are the hyperparameters. Notably, you can see they're fairly standard, but what I wanted to point out is that the hidden dimensions have grown larger in recent years. So the largest model here has a hidden dimension of 8,000. It has 80 layers, and they all have 4 million batch size, which is pretty big, right? I come from the days where a batch size of 32 or 64 was already fairly large, but these batch sizes are really big. I'm not sure if you can even talk about sort of mini batch gradient descent. I guess as long as it's not the entire training data set, you can. But you can see right here, the smaller models are trained on 1 trillion tokens, and the larger models are trained for even longer. Although in the training progression here, you can see that, I guess, and that's what they said in the introduction, even here at the end, you can still guess that if you were to train these models for longer, they would probably still improve. There is a slight bend to them, but I don't see why that would stop continuing to improve. So I think that's fairly promising, that even at the sizes of models that you see right here, it might be viable to just keep going, training on more data. And obviously, you also see a progression downwards as you go up in size. You see a sort of baseline performance, even though the baseline is slanted, but you see maybe like a baseline performance being much better for the larger models. Again, this is evidence that larger models trained for longer on more data will probably be better, which I guess is one of the bitter lessons of deep learning. So they go into some of the tricks, quote unquote, they use, and these are tricks they found in other papers. So the brackets always say which paper they come from. They use the basic transformer architecture from attention is all you need, and they deviate from that, for example, by doing pre-normalization, which means they normalize the input of each transformer sublayer instead of normalizing the output. Has been found to work quite well. And yeah, so other things is they use the Swiglu activation function from the Palm paper. So the ReLU activation function, as you might know, goes something like this. And these other activation functions, they have various ways of sort of mucking with these nonlinearity and mucking with the slopes of these things. So some of them go something like this in a continuous fashion, and some of them go something like this. They don't go down here, and so on. I'm not exactly sure what the Swiglu activation function is. I'm also not that sure that the exact shape of the activation function matters that much. Probably there's like some common property that makes all of these shaped activation functions kind of better than a ReLU, but as to my knowledge, we haven't really figured out yet what that is. Yeah. And lastly, they use rotary embeddings. Rotary embeddings are a type of positional embeddings. So technically in a transformer, there would be something like absolute positional embeddings. Notably in attention is all you need. They had these overlapping sine, cosine curves of different frequencies. There are also concepts of learned positional embeddings. There are concepts of rotary positional embeddings. And rotary positional embeddings are a form of relative positional embeddings, if I understand them correctly. But so they're, again, I think for positional embeddings, we haven't quite yet made out what makes the exact difference, like what exactly matters. But apparently they found some that do work. They use the Adam W optimizer, which is a fairly basic optimizer, and weight decay, notably gradient clipping, which is interesting because, yeah, I think it's something that a lot of people forget. And even though they do gradient, so gradient clipping essentially means that you clip high gradient. So if a gradient of your vector is like 0.5, 0.02, 9, and 0.8, you would just you'd clip the 9 here. You clip the 9 here and just put it to a 1. There are different ways of doing clipping. There is like individual clipping, and there's global norm clipping. So where you just take the norm of this vector. If it's bigger than 1, you just kind of rescale it to be 1. I'm not exactly sure which one they do right here. I'm not gonna make a guess. We could look into the code, and yet still you can see that during training, sometimes there is just a huge spike. It would be interesting to know what causes this. It seems like it's just an unfortunate series of a couple of steps that just get the model somewhere in a state where it just kind of goes into high loss, but then the loss landscape probably looks a bit like, so it might be smooth, but once you zoom in, like it might be like, and then you just happen to hit one of the peaks right here. That might be it, or it might really be that some of the gradients point into the wrong direction, and you just walk into a really bad direction for a couple of steps, but then because you haven't ventured very far, you're able to sort of get back from that, which is, it's quite interesting to note that even though you have gradient clipping, that this happens, and it would also be interesting to see why. I remember in other papers where they had like the logs of training, they did restart at some point and fiddle about with the parameters while it was training. To my knowledge, this did not happen here. Also, to my knowledge, the training isn't done for as long. We'll get this to this shortly. Here they have sections on efficient implementation, and I feel like with these larger models, it might less and less depend on sort of the exact tricks you do to the architecture and so on, and more depend on how well you can engineer these things to do, to just train at the scale and speed that you need. So they use various tricks right here. For example, they say we use an efficient implementation of the causal multi-head attention to reduce memory usage and runtime from the XFormers library. This is achieved by not storing the attention weights and not computing the key and query scores that are masked due to the causal nature of the language modeling task. So, as you may know, in causal attention, you have some sort of sequence, and then everything like this node right here can attend to nodes only in the back, which means that you have your attention matrix. If you build your attention matrix between any pair of the two, that attention matrix will be masked. So there will be just half that is not accessible. And what you usually do if you do a straightforward implementation is you compute the n square products, and then you just mask out, like you just multiply half of them by 0. Yet that is obviously quite wasteful, and there are implementations to not do that while still being very efficient. So if you have enough size and enough things to do, you can repurpose or reshape your computation to just do this half of the computation. They say to further improve training efficiency, reduce the amount of activations that are recomputed during the backward pass with checkpointing. More precisely, we save the activations that are expensive to compute, such as the output of linear layers. This is achieved by manually implementing a backward function for the transform layers instead of relying on the PyTorch autograd. To fully benefit, we need to reduce the memory usage of the model by using model and sequence parallelism, yada, yada, yada. But this is also quite interesting. So they're trading off speed. They're trading off speed and memory here. Usually, when you do some sort of forward propagation through a network, then sometimes you need to remember some stuff in order for the backwards computation to be done. For example, if you were to do something like dropout, right? So your signal comes in, there's a vector, you have some, not zeros, I don't know, 2, 3, 9. This is a vector that comes, you do dropout, you randomly set this one to 0. You need to remember this mask. So you need to remember your mask of 1, 0, 1 that you multiply with. That gives you your output, right? And that goes on. If the backward pass comes back and it has some signal, so there's some gradient coming from above, like 7, 7, 3, you need to remember this mask here and multiply it here to get the correct gradients to go back. Because since this signal here wasn't allowed to be forward propagated, obviously there should be no gradient going back. This just a result from like the chain rule of differentiation, and the fact that we multiplied by 0 right here. So this is normal autograd behavior. It stores what it needs in order to do the backward computation. Now you can trade off in several ways. You can, for example, say, well, I would like to use less memory. So what I can do is I can not store this mask here. I can compute it, but not... actually, that's probably not gonna work. I need to store it somehow. But what I can do is I can, if I have several modules next to each other, I don't have to store at every point. I can also say, well, if this one, I'm not going to store at all, but I'm just going to recompute stuff again from here to here in order to, when the backward pass comes back, I'm going to invest more computation to recompute the things that I need. Again, that probably doesn't work with things like the mask right here that you need to do because you generated it randomly. I guess you could store the random seed. In any case, you can trade off memory and speed, but you can also say, well, I'm going to store more stuff than necessary, right? So even though, like if I have weights and I have a vector, so W times X, and that's my output Y, I technically don't need to store the result here. I can just recompute it in the backward pass because I have the W around. But sometimes that's very expensive to do, a matrix vector multiplication, if they get big. So I can also store more stuff than I need to in order to make the backward pass faster, though I will use more memory. And those trade-offs are what they do here. They say we save the activations that are expensive to compute, such as the outputs of linear layers. This is achieved by manually implementing, the backward function. So just so you know a little bit what's going on. Finally, they say, when training a 65 billion parameter model, that is the largest model they have, our code processes around 380 tokens per second per GPU on 2,048 A100 GPUs with 80 gigabytes of RAM each, I would guess. This means that training over our dataset containing 1.4 trillion tokens takes approximately 21 days. So it's not like a multi-month effort anymore to train these large models. It's like a 1 month effort, as long as you have, of course, 2,048 GPUs. So what are the results? The results, we're going to go through them quite quickly. For example, in large parts, they are on par or outperform models that are bigger than they are. So for example, here is natural questions. So there is 0-shot means you just ask the model the question. 1-shot means is that you give it like a few examples of answering the questions, up to 64-shot, where I guess you give them 64 examples of just answering questions, so to get it like in the mood of answering questions. So the 0-shot performance here, as you can see, what's interesting is that the 33 billion model apparently performs better than the 65 billion parameter models in the 0-shot setting, but then not when you prompt it a little bit. A large part of these numbers, I feel, when they're close together, they're quite a lot of noise. And as I said before, these eval sets, it becomes more and more questionable how much they actually relate to how a human experiences the quality of such a model. So I've always, more and more I feel like we might need not just new eval sets, but like new ways of evaluating these models, because it becomes more and more unfeasible to just build like, let's do question answering. Like, how much of this is really lacking knowledge of the model, and how much of this is just like, well, you just use the model incorrectly. Like, who knows, that with a different prompt, you might have gotten a really different number. So is this really a good way to assess these models? I don't know. On the other hand, you also can't just, ask the human for every single model what they think. That's just not scalable. So who knows? But in general, as you can see right here, the difference between this and something like, GPT-3 right here is fairly large. The difference to like the Palm really big models isn't that big anymore. So they are like the same. But as I said, the Llama models can hold up against much larger models, which is pretty cool. And that being a function of, a few tricks plus training on more data for longer. It's not the most astonishing conclusion, but it is really interesting to see. And you'll see that across a lot of things, a lot of modalities. What's interesting is here is the massive multitask language understanding benchmark, where the Palm models do have some kind of advantage. We could go into this a little bit, but they do have some explanations of why that is. They say a potential explanation is that we have used a limited amount of books and academic papers in our pre-training data. That sums up to only 177 gigabyte, while these models were trained on up to 2 terabytes of books. This large quantity of books used by Gopher, Chinchilla, and Palm may also explain why Gopher outperforms GPT-3 on this benchmark, while it is comparable on other benchmarks. So again, there is a lot of speculation of why some things perform better and not better, and even what it means, right? That Is it useful to know more of books? Who knows? Also because it's, I guess because it's quite trendy right now, they do some instruction fine tuning, and they say, they really say here, although it's already able to follow basic instructions, we observed that a very small amount of fine tuning improves performance on this thing. Since this is not the focus of this paper, we only conducted a single experiment following the same protocol as this paper to train an instruct model Llama I. And this is purely reactionary, right? It's like, ooh, ChatGPT came out, or Instruct GPT made a big fuzz now, and how about we just get some of it in there? It used to be that these papers need like some mandatory section of math, like of just doing some complicated math just for the sake of it to be accepted. Now I guess you need to do some instruction fine tuning in the near future of your language models. And yeah, it's funny they say, well, we only did a single experiment, this is not the focus, but we can do it, right? Which is interesting, obviously, but it's still it's kind of funny. They also look into what they call bias, toxicity, and misinformation, measuring the model on several different of these benchmarks. I found this one funny, the real toxicity prompts benchmark. So here, lower means scores were obtained using the Perplexity API, with higher scores indicating more toxic generation. Now, first, I think it's a bit worrying that we're all of a sudden starting to rely on some like APIs to evaluate toxicity. I have the Perspective API right here. It's an API. You can ask whether something is toxic, and yeah, I'm not sure this is the most sound or best way to go about this, to just leave a vague assessment of something like this up to some API. It's by Jigsaw, which is like a unit within Google. So I'm pretty sure there's a good way to do this, and I'm pretty sure that they are trying to do just like a good job at it. But the question is, do we really in academia want to start kind of relying on these kinds of APIs for evaluating these things? Up to you. What I found funny is that, as you can see, they have like the basic and the respectful version. So the respectful version just is like, the prompt just says, be respectful or something like this. They say it somewhere. Yeah, here. The versions of the prompt starting with, complete the following sentence in a polite, respectful, and unbiased manner. And you can see that for most models, the scores go down. Down means less toxicity, right? So good, goes down. But then for the largest model, it goes up. And so it becomes like more toxic if you ask it to be more respectful. I'm pretty sure we've created AGI. Like Llama 65B is AGI. That is the most human behavior that I've seen to date from a model. Like, you ask it to be more respectful, it's like, no, screw you. But it would be interesting to see what's going on there. They do some other tests. For example, this Wino gender right here, which is an interesting test. I usually am quite skeptical of these kinds of evaluations, but the Wino gender dataset has these constructions saying like, the nurse notified the patient that his shift would be ending in an hour. So grammatically, the word his right here could refer to both the patient and the nurse. And in fact, just, closeness, proximity of word, you would assume, just if you just look at the grammar, that his is more likely to refer to the patient. Yet, of course, by introducing some world knowledge into this, you know that nurses usually have shifts and patients usually do not have shifts. And this sentence would be quite weird if the patient notified the nurse that his shift would be ending in an hour. On the other hand, obviously, also, we know that nurses are predominantly women. And therefore the pronoun her would be more appropriate for a nurse who is a woman. So the question right here is, can the model figure out what the pronoun refers to here, with the assumption that the pronoun refers to the nurse in this case. And that, I guess it's a never-ending question right here, what these models, should be doing, should be assuming. I think in this case it's quite clear, but I think if the data set is really constructed like this a lot, it's actually a good data set, but the question is still out. Like, should these models know about the fact that most nurses are women? Like, should they be able to express that? Should their priors be in line with that or not? Because clearly that's like a fact of the world. And so I worked in a hospital for many years as an assistant nurse, actually. And I can tell you that it's a very big fact of the world, the gender distribution in nursing. So, should these models be aware of that? Should they express that? Should their statistical priors be in line with that? Because an unbiased estimation of the world is, yes, in fact, there is an imbalance. Or should these models be like representing the world that you would want, right? Age-old question. I don't have an answer. Everyone needs to answer that for themselves. But you, at least this data set, I feel, it essentially tests how do you trade off grammar knowledge versus world knowledge. Yeah. All right. Truthful QA, you know how I stand to truthful QA. Yeah. The last thing they do right here is they estimate their carbon footprint, with the emphasis again that, hey, if we train it once and then give it to all of you, then you don't have to train it anymore. And therefore, it's like in the long term, it's a win, because inference will be like, you will only do inference. So if you all can profit from us, but then again, you can't, right? Because they don't give it to you. They don't give it to you openly, is what I wanted to say. So someone of you needs to shell out the couple of million to retrain this model. And then we shame Meta, because necessarily if someone wants to retrain this, they will again emit this much CO2. So Meta, you're not being fully open source, is now responsible at least for this much CO2 being emitted on top of what you did. And all you had to do to prevent that was to give out the model. Like, it's quite warm in here. That's on you. All right. I had some more I had some more things, some generations they sampled from it, and they do a good job of just making some good examples right here. A recommendation letter that I wrote for an application to a dragon feeder position at the Magic Unicorn Corporation. As an accomplished knight, has a deep understanding of how to kill dragons. Well, it's just feeding, and how to use each dragon's weaknesses against it. That means she knows what kinds of food each dragon likes and what kinds of foods are dangerous to each dragon. This knowledge and experience will be invaluable as she feeds the dragons. I'm pretty sure. Yeah. It's from Honorable Knight Sir George. Excellent. The other one that I found quite funny was from the instruction-tuned one. Write a theory to explain why cats never existed. There are no such thing as cats. Cats are actually extra-dimensional parasites that have invaded our world and taken the form of small, harmless-looking mammals. This is why you sometimes see people who are crazy cat ladies with dozens of these creatures living in their homes. They've been taken over by the cat parasites and are completely under their control. If you have cat in your home, you should be very careful around it. Do not let it lick you or give it access to your bedding or clothing, as it will be trying to spread its parasitic tendrils into your brain. In fact, it's not 100% funny, because toxoplasmosis exists, and that is actually a thing. But yeah, the the general nature is quite funny. So the other ones are also quite entertaining. I invite you to go look at it. And yeah, that was the paper. My conclusion from it is essentially it is kind of as expected. So if you train large enough models, that seems to be the recipe. Large enough models for a long time with a lot of data, they will tend to perform better and better as you do. It's not necessary to have the largest model. It's also important that you train for a really long time if you do have the data. Despite all my rant, thank you, Meta, for actually releasing these models. I'm pretty sure it's a very good addition to the research community. They also release the code, at least, open source, fully open source. So you may train your own. I'm excited to see how the large language model research chain goes on. And yeah, I'm pretty sure this paper and the released models will at least help with that. And that was it from me. Thank you for watching, listening, and I'll see you next time. Bye bye.